Hello, year 12. So here's your retrieval roulette for today. So pause the video, get answering those questions. Thank you. All answered? Okay, so there's the answers. 2 was the circuit symbol for a resistor, so it's just a rectangle. And then 4, the circuit symbol for a voltmeter, a V in a circle. The rest of them you can mark from those pictures. So get that done, thank you. Right, so if you open your notes at page 206, please, we are going to start talking about electromagnetism today, okay? So, if you have a bit of wire and you have current flowing through it, then a really, really weak magnetic field will form. So, say this here is just a piece of wire and it was connected up to a power supply and there was current flowing through it. Then we would end up with this little weak magnetic field. So the same idea as the way there's a magnetic field around a magnet, where that's the area around it where the magnetism can be felt. Same idea with this. So if it's just one straight wire like this, then the magnetic field is just concentric circles around the wire. So this wee diagram here is showing that. It is showing you that if you had your wire and you poked it through a wee page and sprinkled your iron filings on the same way you would with a bar magnet, then the iron filings would form these wee circles here. Then if you did the same thing with the wee plotting compasses that we talked about last day, they would show you the direction of the magnetic field, because obviously with this it's not like a bar magnet where there's a north pole and a south pole. Now there's a lot of hand movements in this topic, right? So today everything that we're doing is going to be with our right hand, and we're always going to have it in like a thumbs up position. Okay, and then after that, annoyingly, the stuff is left hand that we're going to be using, but for now, right hand. Okay, so if you put your hand in a thumbs up position, right, and if you point your thumb in the direction of the current, then your fingers, I'll show you here, your fingers will go round in the direction as if your fingers are pointing in the direction of the magnetic field. Okay, so if I take my wire, right, and I say my current, if I'm trying to replicate this diagram here, right, where the current is going up the way, I put my thumb in the direction of the magnetic, or not the magnetic, the direction of the current. And it's like my hand is round the wire, and see the way my fingers are pointing round this way? That is showing me that direction. Does that make sense? Okay. One thing I should have said already, in all of these questions, we're dealing with conventional current, so we're not dealing with proper electron flow. So anytime you are putting something in the direction of the current, it's always conventional current, which is positive to negative. Now, whenever it's just a straight wire like this, the magnetic field is really, really weak, okay? We're going to look at ways that we can make the magnetic field stronger, but this one is weak. A couple of things I just want to point out here. This is just a term I need you to get used to. So magnetic field lines, or lines of flux, choose two different names for the same thing, okay? So magnetic field lines, lines of flux, you need to recognize both of those. Concentric circles just means circles which all have their center at the same place. If you make a point of this, conventional current direction, so easy to get it mixed up here. And then the wee description of what we're doing with our hands there is just down at the bottom. So if you use your right hand to grip the wire with your thumb pointing in the same direction as the conventional current, your fingers will be pointing in the same direction as the lines of flux. Okay, so there's an awful lot of this and stuff like that in this topic. Okay, over on to 207 for me. So one of the things that we can do to make the strength of this straight bit of wire, the strength of the electromagnet stronger if we have a straight bit of wire, is to coil it up. Okay, first of all, we're going to look at a coil with just one turn and what that does to the shape of the magnetic field. Now, this wee diagram isn't great. The arrows aren't like overly obvious in this, so I do need us to just emphasize them a wee bit. So see, if we look at the wire here, this is actually pointing, that wee arrow's pointing down like that. So even if we show that coming down there, like as if it's poking up through a bit of paper, that's the direction that the current is going in. My wee arrow there didn't go in very well. There we go. So the current is coming up here and then down through there, right? Now, these wee arrows here are going that way. So draw them on for me. And then these ones are going this way, the opposite from the one up there, and I'm going to show you how we know that. Okay. So try and make yours a wee bit more obvious the way I have there. So if we do the same thing with our right hand, we put our thumb in the direction of the current and then our fingers are pointing in the direction of the magnetic field. If we look at this wee bit here at A, because the current's going up the way, so we put our thumb up in the direction of the current, and if you imagine your hand is gripping around that wire, that shows you these directions there, because the magnetic field is going to be coming round this way, which is what these wee arrows here are showing. Then over here, because at this point, like if we've coiled the wire over, the current's now going down. So if I'm pointing my thumb down because the current's going down there, then it's like my fingers are going into the page on this side and round the back of the wire. Oh, that thumb, I'm doing that, by the way. Okay. So thumb pointing down and your fingers are going in that way. That's harder to show on this. And then that's why the arrows are going that way. So we need to write in what's happening here. Okay, so if you pause, get that stuff written down for me. Now, this wee bit about in the middle, you can figure out the direction just by using the field lines here and here, because see the way the ones at the top here are pointing to the left and the ones at the bottom of this one are pointing to the left, so it makes sense that these wee middle ones are going to be pointing to the left as well. Okay, right, let's move on. Let's not move on, I forgot to say this wee bit. So this wee loop, this wee one wee singular loop of wire acts like a wee bar magnet. And remember, with the bar magnet, the magnetic field lines go out of north and into south, and that's what's happening here. So it's like this is the end of this is the north end of a bar magnet and this is the south end of the bar magnet. So our magnetic field lines are coming out of north and then going into south. So now let's move on. So this here, wee bit stronger than a single bit of wire, but we can increase it further. So if you get these written in for me here, so again, pause, get written in and all that. So the strength of the magnetic field can be increased by increasing the number of turns of wire in the coil. So here, see the way we've just got one turn? Well, if we had loads of those, it's going to make a much stronger magnet, basically electromagnet. Or if we increase the size of the current going through the coil. So the bigger the amount of current, the stronger the magnetic field that's going to be produced. So that is what we have over on 208. We've got loads of coils here, and then we have a stronger current. See the way the wire is drawn a wee bit thicker there? That's just to represent the stronger current. Now, it can be quite tricky to figure out the magnetic field here, just like on paper, if you didn't have the practical stuff to set your wee magnets or your wee, whatchamacallit, compasses out and all that. So whenever you have your coil of wire, you're basically getting the magnetic field pattern of a bar magnet. Can you see how that's the same as the other one? We've got our wee loops at the top and our wee loops at the bottom, but it's figuring out which end is acting like north and acting like south. Now this here is one way you can do it. I've never really liked it. I'm going to show you how I would figure it out. So let's say we have a spoiler. If you put a bit of iron in the middle, it also makes it stronger, right? So let's say we have a wee iron bar here, okay? And I have a power supply here. If I take my coil, or sorry, my wire, and I wrap it around this, and I'm showing you how I draw it quite slowly here so that it'll help you draw it into yours. Right, so there's my wee wire wrapped around, and I've tried to draw it so that it's going up over the front, and then it's like it's going down the back, and then up over the front and down the back. So hopefully you can see that. So I'm going to just sketch on the magnetic field pattern here, right? So do you remember in that other video I said I was going to contradict myself, because I always say draw 3 field lines. In this wee diagram here it just gets too messy. Oh dear, don't even have room to do all those properly. Oh, mine are touching. Okay, that'll do. So easy enough to remember. If you've got a coil of wire, it's just the shape of a bar magnet, but it's getting what way to put the arrows on that is the tricky bit. So if we go back to our right hand again, only this time we're doing things the other way around. So this time, if we put our fingers, if we point them in the direction of the current, our thumb will point to north. Now, we need to remember it is conventional current, so conventional goes from positive to negative. So that means in this wee diagram I've drawn here, my current is going up here, and it's going up at the front of this and down at the back. So up here, down the back, up here, down the back, up here, down the back, etc. You don't need me to say it for them all. Right, so if I take my hand, let me zoom you out a wee bit so you can see this a bit better. Okay, that's maybe a wee bit better. So if I take my hand, I do my thumbs up, I put my finger as if I'm gripping around this like bar here in the same direction as the current is. So the way that I drew this one, the current's always going up the front. So that means like if my fingers were the coils of wire, the wee bar would be in there, and they're wrapped around in the same direction as the current is flowing. So with my hand like that, then my thumb's pointing to the left, which means that this end must be the north and this end must be the south. And then remember our arrows go from north to south, so they would be that way. Now, where am I going? Into south. I'm going to draw another one just so I can show you the other way round. Okay, so I've drawn this so far. So this time, see the way last time I drew this as if it was going up, this time I'm going to wrap it around the back. Okay, and then it just means we've got the opposite situation of what we had in that other one. Right, I'll draw the magnetic field lines on. So still with the right hand, we're going conventional current, so it's still going this way, only see how this time it's going up the back and down at the front, and then up at the back and down at the front. Okay, so if I get my right hand, do my thumbs up, this time if I am mimicking the current flow with my fingers, then it's going up the back of this and down around the front. And see how now this time makes sense, it's the opposite way around. My thumb's pointing to the right, so that means that this is the North Pole and this is the South Pole, which means our magnetic field lines are going to be the opposite direction from the way they were before. So out of north into south. Okay, so do your thumbs up, mimic the way the current's going around this, so it's going around that way, thumb's pointing north, whereas in this one the current was going up, thumb points to north, over to here. Okay, hopefully that makes sense. That can be quite tricky. You better have been doing the thumbs up with me. It's the only way you'll see what's going on. Okay, this wee one here is as if you're looking at the end. This is just another way to figure out which end is north and which end is south. It's as if you're looking at the end, so you would draw the wee coil the way it is, and then you can figure out north or south. I never use that one. I think it's too easy to make a silly mistake. Okay, so let's look at the wee notes here. So the field pattern should look familiar because it's the same as the pattern around a bar magnet. Yep. In fact, what has been made here is an electromagnet. So another word actually for an it's right there, is a solenoid. So you need to recognize that, because that could be the way it's asked in questions, and if you don't recognize it, you're snookered. and it can be made stronger by inserting a soft iron core. Now the reason it has to be iron is because iron will lose its magnetism easily, right? I'm going to go off on a wee tangent here. The whole point of an electromagnet as opposed to a regular magnet is that, well, you can vary the strength of it, but also you can turn it on and off, so you can use it to like pick up something like a car in a scrapyard, right? Pick it up, move it to where you need it to go, turn it off, and then it's going to drop it to where it needs to be. You can't do that with a permanent magnet, right? Steel and iron are the two big materials here in the magnetic world. Steel, if you turn your electricity off, the steel will stay magnetized for a really long time, so that's why it's no use for an electromagnet. Whereas the iron will lose its magnetism really, really quickly, so that's why it is useful, because then you can actually turn it off. Anyway, back to the notes. So like a bar magnet, a solenoid will have a north pole and a south pole. The polarity, which end is which pole, depends on conventional current direction and how the wire is wound around the core. So the magnetic field direction of a solenoid or a coil can be determined by the right hand grip rule. So that's what we've been going on there. And then that's just showing what I have been doing. So current direction must be marked on the wires, conventional current. And if you imagine gripping the solenoid with your right hand, with your fingers pointed in the same direction as the current, your thumb will point to north. So fingers in the same direction as the current, thumb is pointing to north. Okay, over on to 209. There's a prescribed practical here, but it's actually 3 practicals. I don't know how obvious it is at first glance that it is actually 3. So the first one is investigating the effect of the current on the strength of the magnetic field. So with this, it's always you make yourself a wee electromagnet and you see how many paper clips you can pick up, because paper clips are generally made of steel, and then that means they're a magnetic material, so they'll get attracted to a magnet. So I'll talk you through this wee circuit. So we've got our power supply, we've got a variable resistor, or rheostat is another word for that, and then an ammeter so that we can be measuring the current, because this first one is the effect of current. So we just get a wee coil of wire. Hopefully when we're back in school we can have a wee go at this, right? So it's not, do you know the wires that I used whenever we were building the circuits? It's not them. We have this wee thin wire that then we wrap around an iron nail is what we use here. So what does it say we have here? Yeah, an iron nail. No, it doesn't, it just says it's a core. We use an iron nail. We wrap our little wire around it. Again, wish I brought one home, but I didn't. And for this experiment here, we would keep the same number of turns, and then all we would do would be to change the variable resistor, and that's going to change the amount of current that is flowing. So for our first size of current, we would take our wee electromagnet, dip it into a pile of nails, lift it out, see how many it picked up. You would repeat it, calculate an average, increase the current, do the same, repeat, calculate an average, increase the current, do the same, etc, etc, etc. I will link a wee video. I definitely think I've seen one where someone is doing these experiments, okay, just so you can see them happening. So with that one there, what we're going to find is as you increase the current, the number of paper clips that you can lift up increases, which indicates that the strength of the electromagnet has increased. Okay, the next one then over in 210, same idea, but this time we're going to keep the current constant and we're going to change the number of turns. So we generally go up in tens. So you'll do 10 turns of your wire, dip it into the paper clips, see how many it picks up, add on 10 more turns, etc, etc, etc. Right, so hopefully that's obvious enough. And then this third one, investigating the effect of the material of the core. So you're going to change it for different materials. So there they have a wee list of them there: soft iron, steel, copper, plastic, wood, no material. So iron would be the best. Soft iron. Copper, not magnetic. Plastic, wood, not magnetic. No material, probably will be too weak to pick up. Steel would work, but it wouldn't really let go of the paper clips. Spoiler alert. Okay, so that's a wee quick run through of those, but I'll try and link a wee video of someone doing them, okay? So on 211 there's room for our results. We're going to leave it because hopefully we will get a chance to do this. And then we just have to fill in down here the rules. So the strength of an electromagnet can be increased by increasing the number of turns in the coil. That just means how many times it's wound round. Increasing the current running through the coil. So there's a couple of ways you can do that. You can, like in that practical, just have a variable resistor and then you're changing the load resistance in the circuit, or you can just increase the voltage of your power supply if you have a variable power supply like we do in school. And then inserting a soft iron core. Now soft doesn't mean it's literally soft, it's just the name of the type of iron. So through the middle of the coil, soft iron core, everything wrapped around, and that's it. So we're going to leave it there today, right? The next stuff, so you can see over the page, the motor effect is the next stuff. It is going to start to get really, really tricky. So I need you to be on top of all the information that we have gone through today. So do spend some time doing your thumbs up and fiddling around and everything, and making sure that you know what is going on there. And as always, ask me any questions please if you're stuck, because I haven't heard from you in a wee while. Okay, right, bye.